Hello, can everyone hear me? Excellent. Okay, let's get started. So I'm going to be speaking to you about how we did some research and development into scaling Kubernetes to large numbers of services. At Huawei, we have a fair number of very large commercial deployments of Kubernetes, and before we could do that for some of our customers, we needed to do fairly extensive scalability testing, and we found a few bottlenecks which we resolved. So I thought I would talk to you a little bit about what we did in this area. Most of the hard work here, I must point out, was not done by myself at all, but by my colleague Michael, who's one of our senior research, network research engineers in Seattle. He unfortunately could not make it today. He's sitting in Seattle without a visa, so the task fell upon me to present his good work. This is not a particularly long talk, which is probably a good thing, given that I'm the only thing standing between you and cold beer at this point, so I will take that responsibility very seriously. There should be significant time at the end for questions. I think maybe it's easier if we leave them towards the end, but certainly prepare your questions along the way. We should have a good 10 minutes or so at the end. All right, with no further ado, so what we'll be talking about, as I mentioned before, challenges that we hit while trying to scale services in particular in the topic of this talk, what solutions we dreamt up and considered, some of which we implemented and prototyped to come up with some analytical data to figure out what the best solution was, and we'll have some Q&A at the end. So first of all, not all of you are necessarily that familiar with the way Kubernetes internal cluster service load balancing works, so we'll just go over that. So you're probably familiar, we have a Kubernetes master. Inside the master, we have an API server, controller manager, scheduler, etcd, persistent store, etc. And then we have the nodes, each of which have a bunch of agents running on them, one of which is kube-proxy. Kube-proxy essentially programs a local load balancer on each node, and that then load balances to the pods. So a couple of problems. First of all of the control plane related stuff has potential bottlenecks involved in it. And then once we have deployed the load balancers, the traffic obviously needs to flow through these things, and there are performance issues there too. So deploying services in pods is potential scalability bottleneck. Propagating endpoints, so endpoints are the final IP addresses that the traffic ends up at after load balancing. These obviously change over time when your pods are deployed or torn down. All the changes to these endpoints need to be propagated to all nodes in the cluster. And then the actual data plane itself, we need to add and remove services to the load balancers on each node. In some configurations, that's IPTables. We'll talk a little bit about exactly what the challenges are there. And then accessing the services themselves, each packet in your network stream needs to traverse some sort of rules which determine where it gets load balanced to, and these can also incur performance problems. Diving into the control plane a little bit further, when a service gets deployed, it gets stored in etcd via the API server. That then triggers the endpoints controller, which then creates endpoints, also persisted in etcd by the API server. These are then picked up by all of the nodes, which listen, the kubelet on each node, kube-proxy on each node, listens against the endpoint lists and updates its local load balancer accordingly. Then, whenever we schedule pods, we obviously create a pod in the API server. This, again, will trigger a change to the endpoint, or the endpoints controller will then pick that up, create or remove whatever endpoints might be necessary, which, again, same old story, gets propagated down to all of the nodes. So it doesn't take too much complicated math to work out that if you have n nodes in every cluster and you are trying to schedule some number of pods per second, the QPS against the API server is n times n. That's how many endpoints that's how many endpoints per second are created against the API server. So just to make that a little bit more concrete, you create services. I'm sure many of you have done this before. The structure on the left gives you an idea of what those things look like. They specify things like ports, protocols, etc. Selectors for which pods form part of this service. You get a cluster IP allocated to your service. And then on the right-hand side, this generates a set of endpoints, addresses where that traffic will be load balanced to, and that's the job of the endpoint controller that we mentioned earlier. You can see that that structure on the right is not insignificant in size and can explode pretty quickly if you have very large numbers of services and very large numbers of pods in those services. And that is the thing that gets propagated down to all of the nodes in the cluster, which, you know, as per the announcement day before yesterday, I guess, we're scaling to 5,000 clusters these days. Sorry, 5,000 nodes per cluster. So that can be a pretty significant performance challenge. And then, so not only do you have QPS, but the size of each one of those queries varies depending on the number of endpoints that you have. And in particular, the measured load against the API server is actually the product of the number of nodes, the number of endpoints squared. Sorry, the number of pods squared, essentially. So you can see that that can pretty quickly get out of hand in big clusters with large numbers of services. So we kind of brainstormed a few different approaches to solving the control plane alternatives, solutions. We can partition the endpoints into multiple objects. This, you know, fairly obviously has some pros and cons. You reduce the number of the size of the endpoints, but you increase the number of objects. So the net savings is not very significant. You can also create a centralized load balancer. So instead of having to propagate these changes to all of the nodes, you could potentially create one or more load balancers inside the cluster, and then thereby reduce the number of endpoints that need to be propagated to the load balancers. Clearly, this reduces the number of connections and requests against the API server, but it introduces an extra hop in your traffic routing. You need these things to be highly available. If you only had a single one of these load balancers, obviously if it went down, all of the services in your cluster would go down. That turns out to be, you know, non-trivially difficult. And perhaps most importantly, the scalability of that is kind of difficult because, you know, as you have more services or more service traffic, you need to deploy more of these load balancers and manage them, etc. Now, Kubernetes clearly can make that a lot easier for you. However, if you just have a load balancer on every single node, that kind of scales naturally in accordance with the amount of activity going on in your cluster. So that seemed like a nicer solution. A third option that we considered was batching the updates. So rather than triggering updates on every single endpoint change, we could batch those at some periodicity and therefore, you know, reduce the total amount of traffic against the API server. The obvious downside of that is depending on what you set the periodicity of your batching to, you can end up introducing latency into the updates to the load balancer. See what interesting things we have here. So in that way, we reduce the load against the API server to no longer be proportional to the square of the number of pods, but still n times m. And the QPS similarly gets reduced to n, order of n per second. So let's have a look at some of the data that we gathered in the process here. We had a basic setup with the master for slaves. The details are there, not particularly interesting. But what we did do by introducing a half-second batching delay, we reduced the QPS in our tests by 98%. So that was pretty cool. And if you look at the graph at the bottom, and that's for a relatively small number of services, you can see that our optimized system at the bottom, the red line, is pretty much flat. Whereas with the pre-batching, we ended up with a, essentially approaching exponential growth. You can extrapolate that to the right to 50,000 services, and you can see that the number looks pretty ugly. end-to-end latency. So this is the latency of updating our load balancers. Again, these are fairly small numbers of services. I'm just giving you a flavor of some of the stuff that we tried, and we'll get into some bigger numbers later in the talk to illustrate how this translates when you have tens of thousands of services. I'm not going to go through all the details here. We had a simulation where we had 10 pods in each service. We had hundreds of services across a couple of points of data there. And you can see the before and after numbers. We managed to reduce the latency by 60%, which was good. So the more interesting stuff, I think, is the data plane. So at the moment, the commonly used configuration of kube-proxy is to program IP tables on each node to perform the load balancing within the cluster. For those of you who may not be intimately familiar with what exactly IP tables is, it's a user space application that allows you to configure in-kernel firewall rules, which are implemented on top of NetFilter, which is a part of the Linux kernel. And these rules are contained in things called chains, which are essentially tables, hence the name IP tables. And NetFilter, in turn, is a framework provided by the Linux kernel that allows you to customize things like packet filtering, network address translation, etc. So there are two pretty major challenges related to IP tables, and they're both kind of fundamentally a result of the fact that these things are tables and lists. And you probably remember from your Computer Science 1 courses that inserting and removing from lists and tables is not the most efficient of operations. So when those tables become extremely large, which they do in the case of Kubernetes, you can have some pretty serious problems there. The second related issue is that every packet has to go and match against some rule in that table before it gets load balanced. And if it does a linear traversal through the table to find the rule that matches, if that list is 50,000 long, each packet has to incur that latency, which translates into lower throughput, etc. So those are the problems. Here's an example. So this is the actual IP tables rules that are configured by kube-proxy. In this particular example, we have 2 services. You can see the green ones over there. And for each service, we have a table, which again has a set of rules. I believe that is proportional to the endpoints. Now you can imagine if you scale this up, if you create 50,000 services, that green block near the middle of the screen there becomes very large. And we've got some more detailed numbers in a moment. So what does that mean? Long lists of rules in a chain produce some pretty horrifying things. In particular, so not only do you get poor performance, but you also get variable performance, because depending on where your service landed in that chain, which is probably related to when it was created relative to the other services, the performance can vary quite dramatically. So you can see in the graph there, we've got a bunch of services, so the number of services scales to the right. The first service in the chain is the blue one, and that's the latency accessing that service when you have 1 or 1,000 or 5,000. And you can see on the right-hand side, if you're unfortunate enough to be one of the last services in the chain, and there are large numbers of them, your latency climbs up into the multiple milliseconds range per packet, which is pretty bad. Inside a cluster where you would normally be measuring in microseconds. I don't think it's necessary to go into those details, those numbers much more, but you can see clearly by the hockey stick on the right that that is bad for large numbers of services. So where exactly is this latency generated, and particularly around manipulating these IP tables rules? So first of all, the implementation, and for those of you who might have gone to the excellent talk that came before this one about IPVS, they also touched on this problem where because of the fact that every time the tables need to be manipulated in any way, they need to be locked. If you have multiple concurrent processes trying to manipulate your tables, you end up with lock contention and failures, etc. So one of the common solutions to that is not to actually make incremental updates to the rules, but rather to just update them offline and then upload a whole new bunch of rules with a single lock rather than multiple individual locks. So we copy all the rules, we make all the changes, and we save all the rules back again, which, as you can imagine, has race conditions and other problems associated with it. And IPTables is entirely locked during this whole process. So that, again, when you have 50,000 services and each one of them has pods joining and leaving the service, the rate of change is pretty high, and each one of those operations requires a lock as well as traversals of these very long chains. So you can see the numbers there, adding one rule when we have 5,000 services, which results in 40,000 IPTables rules, details of which we won't go into now, but you could see for the small number of services we had in the example, we had more than that number of rules. It takes 11 minutes to add one rule to the IPTables configuration. So clearly this is not tenable. If you have 20,000 services, you have 160,000 rules, that's 5 hours per update. Obviously not usable. So we considered a couple of different options. One option, which has actually been discussed, I think, before, is the possibility to restructure IPTables into some kind of a search tree. That way you can address both of the issues that we mentioned, one being that any individual chain in IPTables will become much shorter, and secondly, the traversal of those chains. So the insertions are done per chain. So if you're inserting into a short chain, the insertions are a lot quicker. And similarly, the packet traversals through those chains are a lot faster. The other approach that we considered was replacing IPTables with IPVS, IP Virtual Server. This gives a pretty dramatic performance improvement, probably, and we never actually prototyped the restructuring the IPTables option, but IPVS does at least as well as that. In addition to that, it has much smarter load balancing options available. You can do weighted load balancing, you can do retries, etc. So it has much more sophisticated load balancing. IPTables, after all, was not really designed for load balancing. It was designed for firewalls, whereas IPVS was designed for load balancing and can't firewall. So here's just a graphic illustration of what we had in mind for restructuring the tables. You essentially create a tree of IPTables chains, and sorry, my animations are not great here, but you can see that the number of rules you end up traversing is a lot smaller, and the size of each one of those chains for update purposes. In particular, the search tree-based service routing time complexity is order of square root of n, or mth root of n, for a given tree depth. So that's clearly a significant improvement over the numbers that we quoted earlier. A little bit of a background to IPVS, and this is not a deep dive into IPVS by any means, but it's a transport layer load balancer which directs requests. It supports TCP, UDP, and it directs those to real servers. It's part of the Linux Virtual Server project. It's been around for many, many, many years in the kernel. It's very heavily used, considered very stable. So we thought this was kind of worth trying out, see how it works. It's also, like IPTables, built on top of the net filter constructs in the kernel. It supports multiple load balancing, L2 load balancing, which involves MAC rewriting, NAT, IP tunneling, etc. So just to have a quick look at the comparison. So IPTables can manipulate tables provided by the Linux firewall. It's much more flexible, as I mentioned earlier. It does, you can manipulate packets at different stages of the routing process, pre-routing, post-routing, etc. And it has way more operations that can be performed on packets. You can do source NAT, destination NAT, you can reject things, you can do port translations, all sorts of things. None of which we actually necessarily need for pure load balancing. I think the big plus for IPVS is that it's hash-based and rather than list-based or chain-based. And obviously, as I mentioned, it also has a lot more load balancing algorithms by virtue of the fact that it's designed as a load balancer and not a firewall. So you can do least load, least connections, locality-based, weight-based, many different load balancing algorithms. Supports health checks, connection retries, sticky sessions, all of these things of which are very useful in load balancing. If you have multiple backends and a single front end, you would like ideally to have that client directed to the same server for caching reasons. There are numerous reasons why sticky sessions are useful, and we can't do those with IPVS, at least with IPTables. So we haven't released that publicly yet. We're more than happy to upstream the work that we did here. It's a little bit about what we did and how we did it. So there are no behavior changes in Kubernetes. It's fully compatible with the Kubernetes service semantics. Supports all of the normal things you would expect of Kubernetes services. What we did was we made changes to the kube-proxy agent that runs on the nodes. So that agent at the moment already supports 2 modes you're probably familiar with. It's got a userspace mode, which was historically the first one. I think Kubernetes version 1 only supported that. There were performance problems with that and various other things. Later, an IPTables mode was added, which is what we've been talking about now, much faster, all in-kernel, but with all the challenges we mentioned. What we did was we added a 3rd mode, IPVS. The original kube-proxy program was about 12,000 lines of code, roughly. So we added another 680 lines of code to implement the IPVS logic. And it has an external dependency on a CSOR library. So let's have a look at some of the comparative latencies. This, I guess, should be in a graph, but we didn't get there. But you can see that for even reasonably modest numbers of services, if you have a 5,000 node cluster, it's likely that you're running, tens of pods per node. You can imagine that 5,000 to 10,000 to 50,000 services is not unreasonable on a cluster that size, and we do run clusters this big. You can see that the IPTables rule update time is like hours per rule, and if you remember the number of rules that have to be updated for a given churn rate in a cluster, if you're creating and deleting pods, auto-scaling, if you're using HPA, etc., you can imagine that that is, completely untenable. IPVS, on the other hand, irrespective of the number of services that you have, has essentially a linear 2 millisecond update rate, which is by virtue of the fact that it's hash table based and not insertions and deletions from lists. What else did I have to say there? Yeah, I guess that's enough for today. We then ran some benchmark tests using QPerf. You can see that we had various QPS rates, latencies, throughputs, etc. They all show very similar patterns. And you can see the top 2 lines there are the IPVS-based implementation. So we managed to scale it up to 50,000 services. The throughput is, approximately half of what it would be if you had 1 service, which is still pretty bad. And we can do some more work there. I think we can probably get that red and purple line relatively flat, horizontal. The other 2, you can see, even at 5,000 services, which is not a lot, the throughput is pretty bad. And basically, there is no throughput beyond about 10,000 services. So we were pretty happy with that. I guess the other important thing to note there is that the first and the last service in the IPVS case are essentially equally performant, whereas there's a fairly substantial difference between the services, the throughputs of different services in the IPTables case. That's about as much as there is interesting to say on that slide, I think. We've also done a bunch of other scalability work. We worked on scaling the number of nodes and pods in a single cluster. A lot of this work has been sort of paralleled in the open source community for a variety of historical reasons. This was not open sourced, but we probably should have, and will certainly do better in the future with these kinds of things. We reduced various end-to-end latencies. We did quite a lot of work on scheduling performance improvement because we have these very large clusters and pretty high rates of change. We've got an optimistic concurrent scheduler, which actually is a very small change to the existing Kubernetes scheduler. Again, we're happy to open source that and probably will be doing that in the coming months. We also have a pretty interesting flow graph-based high-performance scheduler that we're working on together with the University of Cambridge. And that can bring, very, very dramatic improvements. The optimistic concurrent stuff essentially enables you to schedule multiple pods at the same time. We employ some basic heuristics to reduce the probabilities of collisions. Multiple concurrent schedulers scheduling the same or different pods onto the same underlying resources. And that turns out not to be terribly difficult, actually. If you introduce a little bit of randomization into things, the probability of collision is very low, and then you just retry. And the performance of that was, an order of magnitude or more better than the existing scheduler. Flow graph-based high-performance scheduling is many, many orders of magnitude faster than what we have at the moment, and has a variety of additional benefits, like facilitating rescheduling much better than we do at the moment. And we're happy to open source all of this work. In fact, the University of Cambridge work we're doing is definitely already open sourced, and we will continue to work with the community on that. And with that, I leave you with at least 9 minutes more of beer drinking time, less whatever questions we have. Anybody questions, comments? Yeah? Would you like to grab the microphone there, or if somebody could pass it to him?
How many nodes you had?
How many nodes did we have? Yeah. I believe, and I'm not 100%, in these particular tests that I was, these were very small numbers of nodes. This was just a test to verify. So the performance we expect to, that should be comparable irrespective of the number of nodes. The point of mentioning the number of nodes was just that when you have large numbers of nodes, you're likely to have large numbers of services and pods as well. But we just simulated that by putting large numbers of very small pods on small numbers of nodes, because we didn't have 10,000 nodes to test on. But we do have deployments we have tested in other scenarios with thousands of nodes. I don't have the exact results. I could get them for you if you like, but I think they're in the region of 5,000. We had to make quite a few tweaks to get that to work properly and well. This was, to be clear, this is based on pre-1.6, of course. So I'm sure things are improved in 1.6. Yeah?
So I'm not exactly sure if I understand the compatibility of the IPTables solution. If I'm based in AWS, can I use IPVS? Do I have to have some overlay network to have access to layer 2 or no?
No, this doesn't require any network overlays or anything else. It's compatible. It's a drop-in replacement for the IPTables implementation.
Thank you.
Anybody else? You have 7 extra minutes of beer drinking time.